Okay, today we're going to talk about resolve the motion control for path tracking control. Like what you see here, the robot is following a circular path. So in this control, the path, which is circle, is divided into a number of points. These are called the waypoints. So instead of doing point per control, let's say from point one to point two to point three, in this case, we actually use the velocity, okay, from point one and approach to point two. And so in light of the robot kinematics, the tip velocity is equal to Jacobian time joint speed. And then, you can calculate the joint speed based on the Jacobi inverse for given tip velocity. So here is the algorithm, the resolved motion control algorithm. So in this algorithm, at the beginning, you have to set the initial joint angle. You have to know where to start. And then you generate a bunch of waypoints for the robot tip. And associated with these waypoints, you have to define the velocity. And they have to know the what they call the control time interval here. So TC, T sub C. And the control time is 1 over the control frequency. So I show you this diagram here. For the actual robot control, the signal is not continuous, so you have a bunch of pulses and a screwdriver, and then they control the motor. So the time between two pulses is the TC, so it's right here. So and then you have to go through the for loop, and the n here representing number of waypoints. And then, for example, you starting from point one, and then you want to calculate the joint angle for point two. So use a point one as the base, use that velocity, and then time the Jacobi inverse, and you can calculate the joint speed at point one. And then for point two joint angle is equal to the point one joint angle plus the speed times time. That's the time you're going to travel from point one to point two. So this is joint increment. Okay, so that's called a joint angle updating. Um, yeah, so you're doing the same approach and just going through you just use the same approach. You're going through from point one all the way to the last point n. Okay, so here's a couple examples. The first two, these are the centric circle, which means the center, the base of your robot is right at the center of circle. So in this case, the difference you have the solution one, and this one have solution two, and this configuration is the mirror of each other here. So you can see in this case, actually, you can control the robot very well exactly along the path. So that's not a problem if it's a centric case. Now, if you have a eccentric case, which means the center of the circle is not in line with the base of the robot. So in this case, you will see you start to have an error because this approximation will use the velocity to approach to the next point. So you're gonna have an error. So the waypoints here, and waypoints here equal of 24 points. So the way you're going to increase the accuracy is increase the number of waypoints. Okay, so this one is 48 waypoints. So you can see the error is reduced. So I will show you example in the matlab. You see if you require a large number of waypoints in such a way that you can get very accurate the tracking the tracking control. Okay, so let's see. Go to MATLAB. So this is the MATLAB program already made. So this is RC, IMC, okay, for resolve the motion control. So it starts clear. So if you don't use if you use a radius, and then you have to change your angle to radius. And this is the circle you want to track, and that's the points for you to plot the circle. And here you can define whether it's centric or not centric. So example given to here is centric. The shift, the center shift is on the x is 0.5, y is 0.5, and then you have to calculate xy for the circle, and then you plot. And then this one here is generate the waypoints actually for the rotor control. So I have several choices: 24, 48, and the 300. And from here, then this is the waypoints you generated. These are control points generated x, c, y, c. And then here you can define your control time here. And from control time, you can define your omega, and then you can define your tip speed. So in other words, your tip speed has to be defined. And then you define your robot, the link length here. And for the because I give the initial position, so here. So if the initial position is the given, and you can solve. Well, because I start with for the circle, I start with the first point. So I take the first point as the initial position. So from there, you can solve the initial joint angle. If a joint angle already know, you don't have to solve it. So since I start from the first point, okay, so I don't know the angle, I have to solve it. And then you plot the first initial configuration for the robot. And here you're going to the IMC control, and you have to go through all the waypoints, okay? And then you have to draw a circle, and then you plot the waypoints. And here, so I want to record the current draw angle, okay, current draw angle. And this is the current drawing, the current robot position. And then here you start to you have to go to next step, right? Next point. So you have to calculate the Jacobian, and then because I defined the tip velocity, total tip velocity, and it had projected on x direction and y direction, okay, becomes a vector. And then here you determine the joint speed, and the joint speed, okay, and then here from joint speed. So this two is equal. Okay, I just save it, and then this is the joint speed time, and you give the joint increment plus the previous joint. So your joint angle is got updated, and then that's it. You just go through all the waypoints, and then you will have the path control. So I show you here, you will have 24 points. So it's a little bit rough. So showing here, it's a little bit rough here. Okay. Because approaching, right? It's approaching, not exactly hitting the points. So let's say we give 48 points. So it will be getting better, but still not that accurate. So if we have a large number of points, larger points means your control frequency has to be really, really high. So usually local control frequency is around 500 hertz. For 500 hertz, of course, you can do that, which means within a second, and you have even 500 times to updating, right? So that's what it means. So that's very fast. So you see here, so that's why it's very accurate. So exactly follow the circular path. All right. Now you learn how to use the resolve the motion control. Actually, you can control the robot, follow the path. Okay. Thank you for watching.